going to be a new chapter. Miller effect.
Is this the last chapter?
Yeah, the second last, I guess. So if there's a cab, this is for modeling all the digital systems, so you understand where the time delay comes from digital circuit. It's kind of important. If this one is a digital circuit, so it's 0 to VDD. Okay, and on the other side, you got another power supply. It's just a model, it's not a real circuit. It pulls current from the cap or charges from the cap. It's discharging the cap. At the same time, so this VDD to 0, this is 0 to VDD. It's a little bit different than the other circuits we have seen, right? It's just one charging and discharging from one side. But this is doing from both sides. Why do we model it that way? Because if you look at the cap, the NMOS, VDD is here. This is a resistor. This is a VL. I've told you that there's a parasitic capacitance here from the gate dielectric material, right? You can model it in two halves of the cox, which is capacitance of the oxide, right? So if there's a NMOS, and there's a dielectric material in the middle, and wire, and this is a substrate, definitely connect to the wire, to the ground, right? So I have two, like considered as metal plates and dielectric material in the middle. So the textbook models this gate into two halves. So it's a half of cox. It's the capacitance of the oxide layer. This on the other side is another half of it. Okay, so these are the two caps. There's no physical caps being shorted to the gates. It's ridiculous. Why do you do that, right? These are models. Okay, so what's the size for each capacitance? Capacitor here. Yeah, half of cox, right? Physically, right? If there's nothing charging and discharging it. But if you turn it on here, so this part is gonna discharge this point, which is the other side of this cap at the same time. So this will give you the Miller effect, which is, you know, if you charge and discharge one part of the cap, for example, the capacitance is C for this capacitor, and the voltage change, you know, just one side, right? The voltage change is VDD, and the capacitance change is C. No, the capacitance is C. So what is Q? What's the delta Q here? The charge. Victor and Charlie, right? VD times C. Okay. However, this capacitor is not just shorted to one source; it's also shorted to the other source, like this circuit here. 1, 2. You got a VDD here, and you got a digital signal is considered another source. It's charging, discharging at the same time. So for this part of the cap, it is discharging this capacitor. So the delta Q, you got another delta Q, which is another VDD times C. So the delta Q, instead of 1 Q, if you only have one source, it has 2 Qs. So the overall delta Q is 2Q. I couldn't visualize it. This is what the textbook tells you, right? It works for the simulations. Anyway, so if you just do it one side, it's just Q, right? If you do it, so because this is charging, this is discharging at the same time, you have two power sources, it's superimposing to each other, right? So got 2 Qs difference in there. And only one, yeah, but you know, only one VDD happens here. So the overall voltage change is VDD. It's VDD and to 0. It's only one VDD takes place here, but 2 Qs. So the overall capacitance instead of C is effectively 2C. If you look into it from one side, from each side, if there's a person here, you look from this side, it's going to be a 2C instead of 1C because of the mirror effect, which is you charge and discharge at the same time on two sides of the capacitor. It's called mirror effect. And give you effectively 2C here instead of 1C. Yeah, I know I couldn't visualize it, but that's what happens. Why is different? If you have one here, right? You got this. It's RC circuit we have been doing for a long time. This is tied to the voltage. It's not changing at all, right? It's only changing the voltage here on one, charging on one side. But this is different because charging and discharging at the same time. So changing more Qs.
I mean, isn't that one on the right also discharging? Is on the fault.
But it's different. You can tell it's different, right? Because this one got more power over there. So it used to be, before it does that, right? It used to be minus and plus because this was 1. So it's flipping. It's not just canceling it. It's flipping it. So this one at the very beginning, it was 0 and 0, right? And eventually when you charge it up, you got VDD and 0. But this one was 0, right? Yeah, if this one got plus and 0, it's going to be the same effect.
So the voltage source on the left would be a sine wave, and the one on the right would be a cosine wave. Switching. Is that what?
It's not sine wave, it's a square. Yeah, similar. Yeah.
Okay.
Yeah. Because the power source can do it, right? There are sources. Sources can do whatever they want, defined by the manufacturer. So this charges up and this discharges on the other side. Just doubles that charge change. So it becomes 2Q over VDD. So effectively it's a 2C from each side. If you look from each side, it's 2C. We modeled that circuit in this way because for the NMOS, exactly the similar thing happens here, right? When you open it up, the channel is opened up, so it's discharging this part from VDD. You got a resistor is limiting, so it's not shorting ground to VDD. This charge from 0 to 1, and this becomes 1 to 0 because it's opens up the channel and pulls it down to ground. So when you model the capacitance here and for the output, you're gonna follow the mirror effect. So for here, the equivalent circuit becomes that's VDD, still VDDs, but this is 2C and 2C from each side. When you calculate time delays, you need to use 2C instead of 1C because of the charge change. It's different from the ones has one source in there. So what's the effective capacitance if you look into this node? Looking inside, looking into it. It's going to be twice as much as this one, right? Plus this one.
Yeah.
So if you consider the Cin is the input capacitance of the inverter. This one has a mirror effect. What about this one? No, it's tied to the ground. It's not changing as this one changes, right? So this one doesn't have a mirror effect. I have to divide it into two halves because this one doesn't have that mirror effect, but this one does. Got it?
So the total capacitance would be 1.5.
C equals this much of 3/2 of the cogs, right? important. It's not just for this class, right? It's important fundamentals of the circuit design. Is whenever you are calculating capacitance, you have to consider that Miller effect. It's everywhere, not just here.
So we pay attention to that if both sides are receiving a charge.
It will.
Right, but like we should be the Miller effect only takes place when both sides are being charged.
Yes.
Because it charge and discharge.
Charge and discharge got two sources happening in the opposite way, right? So it's doubling that effect.
Right. If one side is tied to ground, it's something that's not receiving charge.
The same cap. Yeah. It's important to know that, because whenever you are calculating the time delay from this point, you got to know what's the effective capacitance. That's why we need to model it that way. Okay. What about the capacitance over here? How do we model the capacitance over here? What's the capacitance here? Just think about this circuit. You know, if the two nodes are being connected by this one capacitor, it's being modeled like this, right? So you got two 2Cs on each side. So here's the circuit, same thing, one node, one cap, one node, right? If you model it, you have to split this one, and for each side you got you got twice of this, right? Which is one cox. So one cox here, one cox here. So what is this?
Why are we putting this in?
Oh, I'm modeling it. So this is this one. And I didn't draw it, but there will be an effective capacitor for the input here as well, which is 2 times 1/2 of cox.
The node in the middle of that discharge to ground.
Yeah, let me redraw it. So for this circuit, okay, so here is a capacitor. You know, this capacitor doesn't have mirror effect, so we are not calculating this one at all. So when we are calculating the C the input capacitance, we directly add this one to it. Okay, but this one does have that mirror effect, and this capacitor is like this capacitor in the model, right? And for this model, we divide into 2 caps, and which one is 2C, right? So for this one, we should divide into 2 caps, right? So one is connected to the output.
Wait, can you explain to me where that second capacitor is? Oh, wait.
This one?
No,
This one?
Yeah, that one.
This one is, you divide this one into 2 caps. This is this
That's
one.
just from the model, right?
Yeah, on the right hand side, right?
Yeah.
And you split this one into the 2 halves, and the one on the left, which is you know, the mirror effect cap. We didn't write it here, but it's going to be another one connected to the ground, which is cox. So this one, we draw it here, but actually this one is getting removed and being replaced by this and this, according to mirror effect. So what's the capacitance here? No. Yeah, you got a half, right? You got a C here and 2 C's, 2C for on each side, for according to mirror effect. 1 C here and 2 C on each side. You got 1/2 cox here, so you got a cox here. Make sense?
Mm-hmm.
So this will be replaced by these 2.
Why would that capacitor not be? Why is that capacitor by the V out instead of by the VDD?
What do you mean?
That red capacitor,
Yeah.
like on your model on the left,
Yeah.
it runs through VDD instead of. Never mind, I'm confusing myself.
That's the discharge.
VDD is here, right?
Right, so that's our second power source. The model on the left has the second power source.
Mhm.
Sort of to the other end. So why would our
Oh, because I You just measured it, right? It's the same thing here and here. It's either way, it doesn't matter. If the parcels here or parcels here, it's same thing.
Okay.
So this one is being replaced by this and this, right? So now you can tell from this point, these two are in parallel. So C in is, again, 3/2 of cogs, right? Okay, so CL from this output point, from this model is just cogs. If there's a, this is the model, this is not a physical capacitor again, all right? But in the real circuit, there might be a low capacitor, CL. So what's the CL totally if you've got a CL here? Yeah, because they're in parallel. Make sense? It's okay if it doesn't make sense. I'm still keep moving forward. Yeah. All right, so if you understand that, it's going to be easier for all the calculations later. I'll probably have another homework assignment after today's lecture and also next week's Monday, Wednesdays. It's going to be simple. It's okay. All right. And we know that as an NMOS, when it discharges the cap, this is a C load, okay? It discharges the cap through that channel and it follows a curve because this is BDS, this is ID, right? That's a curve. And originally, if this model stores VDD over here, so VDS originally equals VDD. That's VDS, right? And that's VDS. So VDS equals VDD, that's the original value. And start discharging it, it follows this curve. That's the IV curve of the transistor. It's going to follow that curve, definitely. But however, we model the channel resistance using a linear resistor. I know it's not accurate, but this is how it was modeled. So Rn equals 1 over the slope. Approximately, not exactly. Okay, so Rn equals what? 1 over, yeah, 1 over the slope. And so 1 over slope is what? Is VDD over ID. Which is VDD over KPN over 2 width over length VGS minus VTHN squared, right? It's a square law equation. Okay, so now where our Rn comes from, but all the parameters for Rn, these are provided on the textbook. So in the future, I'm going to provide this parameter to the right behind that problem description and directly use it. You don't know this one? Okay. Look at the model. I think for the two of you, you have seen the similar things in analog. So for NMOS, what's the model circuit or DC model? Maybe it's slightly different from the ones you saw there. So here's a drain, Rn. That looks odd. That's NMOS.
Yeah, to see this. What is that floating point to the left?
That's the gate.
That's a gate, yeah. So when the gate got a voltage, it closes a switch. So flow the current to Rn to ground. You'll be used to it if you have taken some microelectronics 1 and 2 and 3 in the future. I've been use it all the time. No, microcontrollers is Arduino. Yeah, microelectronics is analog 1. You guys are doing it's called microelectronics 1. But here we call it analog electronics since we don't have her. Okay. That's the model. Let me see. Okay, so including the caps. If you include the caps into the model, it looks like this. Rn switch, one here, one more here. Here's VL, and that's ground. That's Rn. That's Cin. That's a gate. That's a capacitance, effective capacitance for here, right? Cin. And here's G. Where's drain? This is drain. That's source. What are these? What is this? What is this? A quick question. What is Cin for the animals? So what is this? No.
Oh, wait, no, that'd be 1 and then.
Yeah, 1. Yeah.
Oh,
All right. So we use for calculating that time delays.
Is that the only thing that you for time delay? Like you wouldn't sit here and try to figure out capacitance.
Yeah, you'll see a couple examples. Yeah. And another concept here. That's input, that's output. Being delayed horribly here. Remember 50%. 50% amplitude, okay? 50%, 50%. So this is called T, the time delay of propagation delay. TP, if you are looking at the output, if this is low to high, it's called LH. As the output, right? This is VL. That's V. Always look at the output, okay? Sometimes it's being inverted, right? So the input or output has a different chain transitions. So always look at the output to determine is LH or HL. So for this one, 50% as well, right? So this time delay is called TPHL because the output is high to low. By chance, this one has the input has the same transition, but always look at the output, right? These are the two time delays. So these equals determined by the capacitance. You are looking at the input or output. So, but overall, the time delay is always 0.7 RC, right? This is something we know. It's easy to calculate. You just need to find out what are the R's and C's to calculate the propagation delay in the circuits. Superconductance or superconductors. Example, let's look at the example. This is on page 320 of the book. So for NMOS, PMOS. This is 10 micro by 1 micro. If this is the size of the transistor, right, 30 micron over 1 micron, then the Rn equals 1.5K. You can imagine, right? Because if you got a longer transistor, you got more resistance. Okay, this is 1.5K as well. And Cox, this is 17.5 femtofarads. This is 52.5 femtofarads.
Do
Right.
they not have different oxides in between the gate? They all have the same.
This is larger, 3 times larger
Well, right,
by
but
area.
I mean,
different manufacturers don't use different
Yeah,
oxides.
definitely it's different, right? Different process has different thickness of the gate, of course. Yeah. And if this is the circuit, it's discharging the cap through the channel of the NMOS. This is 50 femtofarads, that's C load, okay? Discharging it at some moment. And this transistor is 10 micron over 1 micron by size. So we'll turn it on, right? It's going to start discharging the cap. So what's the time delay here? HL, LH. Yeah, but which one you want to use? You want to write, hey, TP, HL, right? Because H to L. VL was H. It's discharging it. Equals 0.7 RC. We have to know what is R, what is C here. It's the NMOS is 10 micron over 1 micron, so we can directly use it. 0.7 times 1.5K, right? So what is the capacitance?
Wait,
Just 17.5. Because it's just the Cox when it's going through the.
Mhm.
Is that good?
Yeah, it's just, let's look at the model again,
The Cox is.
right?
Yeah.
So as the output pin here, the C total equals, I write it down here, right? Equals this Cox plus CL.
why do we not care about the two? Why do we not care about the two in the gate?
Because we are looking at the out, so we don't care about the V in.
So 17.5.
So if you model the circuit, it looks like this. Right, C in is something else. We are looking at the node, which is VL. So I only care about Cox and CL and Rn here, right? It's going to be Rn times Rn is going to be 1.5K, and C total is times the C load, right? And plus the C load. I'll calculate it, right? Okay. The circuit here, right?
Oh, I guess
We don't really care
don't
about.
have anything going into.
No.
I see, we have no signal
No, so usually the low to highs happens for the PMOS because PMOS is better at conducting VDD, right? So that's why for the CMOS technology, we always design PMOS on the top to do that L to high stuff, right? So you have to care about the RP and Cox P. Yeah. So now let's look at the PMOS. How do we model a PMOS? VDD. VL is here, it's green. So this is a half of Cox, right? If one term is tied to VDD, so it's not changing on both sides. So this one has or doesn't have that mirror effect. Yeah. But this one has, right? This is C load. And I forgot how the textbook drew that equivalent circuit, but I remember it didn't make too much sense to me. So I redrew it in a slightly different way, which makes more sense. CL, Cox, RP, that's C in. So what is C in here? Twice of this one plus this one, right? Yeah? Yes.
Wouldn't it be twice that one plus CL?
No, C in.
Oh, we were talking about CL last time.
Okay.
So this is 3/2 of Cox, and this is still Cox, and you got a CL here. And so what is TPLH? 0.7 times RP times C total here, right? So RP is given, but I will throw these parameters here, 4.5K. And Cox P is 17.5 femtofarads for because this guy is 10 micron over 1 micron. You know, from the table, see, it is given, but this is 30 over 1, and then it is 52.5 femtofarads. But this is smaller, right? Smaller area. How much smaller? 3 times smaller. Just a third of this one by area, right? That makes sense?
Yeah.
Yeah. So capacitance equals what? Epsilon times A over D, right? So D is not changing. Determine the precise. And A changes. So the capacitance is going to be 3 times smaller, right? So C total here will be 17.5 femtofarads plus CL. What is CL? I put here 50. Why is 17.5? Because this is 52.5 divided by 3. All right. If is the resistance changing? It is, right? Because it's wider. Yeah. Wait, it's wider. So the resistance becomes it's shrinking, right? So this is shorter. Yeah, the wider one got less resistance, right? So the shorter one got, so for example, a resistor here. This is a resistor, right? In that flow current in that direction. And if you got 3 times wider one, it's going to be less resistance because R equals this, right? So we got more A, but less resistance. So that's why this one has less resistance because it's wider. It's equivalent to 3 resistors in parallel. So this one has to be 4.5K instead of 1.5K, right? Okay, pretty simple. Just multiplication, division. Here is calculation at middle school level. So sometimes if the load capacitance can be pretty high compared to the, especially when we are using 180 or even smaller, like 40 nanometer technologies. So the capacitance can be even smaller because the channel, the size, the footprint of the transistor is smaller. So the capacitive load can be relatively higher compared to this one, compared to the channel capacitance, then you can ignore this one, only consider the low capacitance. So for example, if this one becomes 5,000 femtofarads or 5 picofarads, then you got 5,000 femtofarads adding like 17.5 femtofarads, you can ignore it. It's not contributing too much delay. Directly use 5,000, right? Don't bother like calculating all the small capacitance. So what about the inverter? If you look at the inverter, it's not a single transistor anymore. So we got 2 of them. Cap. What is C in? What is C out? Let's write it down first, okay? Oh yeah, I will. Yeah, I will do that. Physically, these are half Cox, right? But this one has a mirror. This one doesn't have a mirror effect. This one does, right? This one does as well. So C in equals Cox. This is Cox P plus Cox N plus a half of Cox P plus a half of Cox N, right? So this is, wait.
1.5 Cox P plus 1.5 Cox N.
Which is 3.
Yeah, so
Oh, yeah, you're right.
Yeah, they may have different sizes, right? Different channel sizes, different width and length.
That means you guys are also wrong.
Oh, yeah. The first one.
Is that correct? Yeah.
Kind of is holds true if they have the same capacitance.
Yeah. All right. What is C out?
So way more difficult. So that's
No. What are these caps contributing to C out? Which ones? The top?
Wait, what? Oh, no, because that's not me. Okay, yeah.
Yeah. So what is C out?
Yeah, CX N. Yeah.
Oh yeah, plus low. Yeah. We don't have low. I didn't draw a low. Make sense? Okay. So for inverter here, what is TPHL? HL. HL, which one is doing that job? NMOS, right? So this is 0.7 times Rn. That's the channel resistance of the NMOS times. So for this one, you are looking at which node? VL.
Oh, I guess it would be our C out.
What is C out? Yeah. Okay, so TPLH equals, do they have the same COX, CL?
Yeah.
Yeah, same node. Okay.
The only thing that changes are the distance
Yeah.
between.
Yeah, it goes through different channels.
Oh, just multiply by 2, right?
No,
Oh, that's so lame.
that's
Oh, because our CN would be.
yeah.
Our
That's C in and CL, right? Yeah. How to draw that? You know, the models. So an inverter. So for the inverter, right? For the inverters, here's the input, right? And it has one cap here, one cap here. These are the two input Cins. 3/2 of Cox P, 3/2 of Cox N, right? And then there's no connection because that's a gate. And then you got a switch for the channel resistance and switch and channel resistance. That's RP, that's RN. And here's the output pin, and that's CL, that's Cox P, Cox N. That's one inverter.
Why is it not? Oh, I see. I thought you were starting to do.
We need another inverter. Is there a physical connection in between the output of the first inverter to the input of the second inverter? Yes.
Didn't Tesla invent wires electricity?
No way.
Talking Colorado Springs.
So he's shooting it.
Right. So when you, so what's the C total here?
Total there is the.
Just add all of them together.
Yeah, just
Wait.
5/2 Cox P plus 5/2
Right, adding these two together and these two together as well, and overall. So when you calculate the time delay here, you have to consider the C total here. So, what is TPHL? Let me know which channel is working here. Yeah, which one most?
Oh.
Oh, there's nothing. There's no connection. It's a gate. This guy.
Oh, because we're looking at the.
Yeah, so this one, the switch is going to be closed and so discharge through this channel. You got two inverters shorted together, right? Keep in mind, only this guy's NMOS is discharging this point to ground whenever it goes from H to L, right? So this becomes 0.7 times what? And these Rn, right? Okay, and times C total, right?
You're not taking into account the.
No. No, this is C in, right? If you look at this node,
Okay.
these are only the 4 caps physically shorted to this node, and this is only resistor shorted to this node. This is switch is off, right? TPLH equals 0.7 times this RP. If they have different RPs, okay, can be different sizes, but it's going to be this RP times C total. And this looks like what? I mean, it reminds you about what?
A wire.
You didn't do the ring oscillator?
Oh, yeah.
Did you wonder about like why it oscillates? Why the ring oscillator oscillates? Yeah.
Couldn't you just put like a bunch of resistors and capacitors in it on the same thing?
No, you have to invert it.
Oh,
Yeah, we are going to show why it works on Monday. Okay, and how to calculate the time delay for the specific ring oscillator. You have 7, how to calculate the time delay. Okay. So,
You're not coming in?
yeah.